question of why certain elements in the periodic table are ferromagnetic. We're kind of moving away from our description of free electrons, even though we have dealt with free electrons that are also interacting with one another. And now we're going to move on to the last module of our course, which is on band magnetism. What happens to electrons that are inside bands within a solid, and how can they give rise to ferromagnetism? So this is the last module in our course. This is our third last class, in which we're going to cover new material to talk about band magnetism. So if I look at the periodic table, and I look at the period number 4 of the periodic table, it starts with potassium, calcium, and then there is scandium, chromium, vanadium, chromium, vanadium, titanium, nickel, cobalt, manganese, nickel, cobalt, nickel, cobalt, manganese, copper, and probably scandium. Can anyone check this, please? Does anyone need a proper ordering? So if you look at the electronic configuration of these elements, this is atomic number 19, atomic number 18 is argon. So the electronic configuration of these atoms starts after argon, which has 18 electrons, 19, 20, 21, and so on. Here the 3d orbital starts to become populated. Okay, so now the question is, why are these 3 elements only in the periodic table that are room temperature? At room temperature, gadolinium and dysprosium are 2 other elements that are rare earths that can also become ferromagnetic at very close to the room temperature. If you cool down to say 0 degrees or 5 degrees centigrade, francium, which I think is an alkali metal, also gets ferromagnetic. So why is it that these 3 are ferromagnetic predominantly? Why do they form bulk of the magnetic materials that we are currently accustomed to? All 3 of them are, by the way, soft magnetic materials. Now, in order to understand this, first of all, we would like to look at the Stoner model. So we're going to start a discussion with the Stoner model. The Stoner model is kind of in between free electrons and bands, electrons that are inside bands. Now, if you look at the Hamiltonian in the Hartree-Fock approximation, this was given by sum over k's sigmas h bar square k square over 2m ck sigma dagger ck sigma, and a potential energy term minus u, some potential energy, Coulombic energy u, sum over P1, P2, and sigma, which is the exchange interaction term. And we have n number of electrons, a number operator corresponding to the number of electrons which have momentum p1 and np2. Okay, so this was our Hartree-Fock approximation. In fact, I would like to use capital N's here. Total number of electrons, number of electrons. And we also want to integrate over the 2 kinds of spins. We also know that we can approximate this Hamiltonian gave us the approximate energy 3/5 n plus EF n plus ये हमने देख लिया था ना पिछली दफा plus 3/5 n minus EF minus ये देख लिया था, इस तरह हमने ब्रेक डाउन कर दिया था पिछली दफा क्लास में, ये शायद नहीं किया, जरा देखें अपने नोट्स। Stoner model. This model, by the way, is from 1936. One of the earliest models that describe ferromagnetism. Now, if you look at this, just this term here, I can break up this interaction term between the electrons as sum over P1 n P1 sigma sum over n P2 sigma sum over sigmas, right? The two kind of spins, correct? So if I define this is just the number of spins, total number of spins which have a spin magnetic moment of plus of sigma, and this is also the number of spins that have the same spin sigma. Sigma could be plus 1 or minus 1. Spin up or spin down. So this summation can be written as n sigma squared, correct? Over the two kind of spins. Now this means that this summation is really n plus squared, the number of spins with spin up squared, plus the number of spins spin down squared. Correct? So now what we're doing is we have two kinds of spins inside the system, up and down. This is the total kinetic energy for the two spin sectors. You see, sigma could be up or down, and there are two kinds of spins, up and down. So the kinetic energy, the band split up into two parts, two spin sectors, up and down. Okay? Now if from this Hamiltonian and from this prescription, I could now write down the approximate energy, the Hartree-Fock approximation for this spin split system. Remember in the previous lecture, I talked about polyparamagnetism again, and so described how the spin sectors split up into two bands. So exactly the same kind of mechanism is at work here. So now the total energy, unfortunately the chalk here is not very nice today, so but let's make the best out of it. So the energy in the Hartree-Fock approximation is now given by, this is the total kinetic energy of the system, the first term. Okay? This Ca sigma bracket Ca is the total number of spins of wave vector k, electrons of wave vector k and spin sigma, right? So you just multiply this with the kinetic energy of each one of these electrons, okay, the total kinetic energy. So that kinetic energy is now split up into two parts, spin up and spin down. And we already know that the sum of this is given by 3/5 times n, where n is the total number of spins. But now we're going to split this up into two parts. One part due to the upward pointing spins, n plus, and the Fermi energy corresponding to those upward pointing spins, plus the kinetic energy due to the downward pointing spins. multiplied by the Fermi energy due to the downward pointing spins. Because now, if you remember, the spins are aligned with one another, the Fermi energy expands or contracts, it expands really. So this is the kinetic energy term in yellow, minus U over 2 n plus square plus n minus square. Alright, so this is our approximate energy for the system. Again, potential energy term and a kinetic energy term. Now, in the previous lecture, we described if you had perfect line cross spins, under what conditions does the negative term, which is the potential energy term, outweigh the positive term, which is the kinetic energy term? So, under certain conditions, which are conditions imposed on the number density of electrons, Rs, does this potential energy outweigh the kinetic energy, and you get ferromagnetism. Now we would like to look at an intermediate situation. The intermediate situation is that we have some positive pointing spins and some oppositely pointing spins, and we have some polarization. Right? So there's not complete alignment, there's partial alignment. So we take this kind of parameter to tell you what's the net polarization between upward pointing and negative pointing spins. We normalize this, and let's call this some zeta. Okay? ये हमने पिछली दफा भी डिस्क्राइब किया था, अगर आपको याद हो. Alright, so this is our zeta. We already know that m is the total number of spins, okay, in both the spin sectors. We also know that this is 1 plus zeta raised to power 2 by 3, raised to power 2 by 3, correct? This is 1 minus zeta raised to power 2 by 3. Correct? By the way, it's not the modulus of zeta. It's not the absolute value, it's just zeta. Right? So now what we have is, under these conditions, we also know that given this and given this, we can also know that n plus is n by 2, 1 plus zeta. Correct? And if there is a minus sign here, this is a minus sign. Okay? So with all of these kind of substitutions, the energy in the Hartree-Fock approximation for partially polarized spin alignment, which is the general case, is going to be 3 over 5. N plus is m, 1 plus xi, and you have 1 plus xi here. This is EF, 1 plus xi, 2 by 3. This gives me 5 by 3 here. Plus 3 over 5 n EF, 1 minus xi, 5 by 3. Correct? Minus u by 2. Now this thing is n squared 1 plus xi squared. If I kind of write this sum, I can break this down. I can express the energy in totally in terms of n and xi instead of n plus and n minus. So this is what this term will look like, correct? Let me quickly check this. So I have n plus n minus squared, which is n squared. This is n plus squared plus n minus squared plus 2, n plus n minus. I have n plus minus n minus squared, which is n squared, just squared. N plus squared plus n minus square minus 2n. So I add these, I get this plus this divided by 2. Right? So there is a additional factor of 2 here will be 4. Alright, so this is my energy for the system. Now, when will there be ferromagnetism? Spontaneously, no application of magnetic field so far. We haven't applied any magnetic field, correct? So this is all spontaneously happening without the application of an external magnetic field. Now, under what condition can you imagine that this energy expression is going to give me spontaneous ferromagnetism? Spontaneous magnetism is ferromagnetism or ferrimagnetism or antiferromagnetism. It can't be paramagnetism or diamagnetism. So what's going to happen if, under what conditions, by looking at this equation, can you tell that spontaneous ferromagnetism exists? What is the condition for ferromagnetism? क्या?
उसकी intrinsic property.
It is a property. तो कैसे इस इक्वेशन को देख कैसे हमें आइडिया हो सकता है? ग्राउंड स्टेट उसकी फेरोमैग्नेटिक में चलता है. ग्राउंड स्टेट कब आएगी? जब एनर्जी मिनिमम होगी. तो मैं देखता कि ये एनर्जी कब मिनिमम होगी. उसके लिए मुझे इसको डिफरेंशिएट करना पड़ेगा. अगर ये ऐसी हालत में मिनिमम हो जब मैग्नेटाइजेशन या पोलराइजेशन नॉन जीरो, when this term is non-zero and this is in its minimum state, then I can say that spontaneous ferromagnetism is possible. Spontaneous ferromagnetism does exist. So I really want to differentiate this energy with respect to Xi. Because Xi is my parameter. If a minimum for this energy exists at non-zero Xi, then ferromagnetism is a stable state, is the ground state. It will be minimum. It will be like, if I draw this energy curve, there will be a trough. If that trough exists, the minimum exists for non-zero Xi, then I will have spontaneous ferromagnetism. So I need to kind of differentiate this energy with respect to Xi. ठीक है ना? जी.
सिर्फ ये आपने कर लिया और लेट्स से वो हमारे पास नॉन जीरो आ जाती है. अब वो एक स्पेसिफिक प्रोटॉन नंबर्स पे डिपेंड करेगी ना, मतलब क्योंकि हम ये अस्यूम कर रहे हैं, हम ये कह रहे हैं कि फिजिकली हम देखते हैं कि ये तीन मेटल्स रूम टेम्परेचर पे लेट्स से फेरोमैग्नेटिक होते हैं, ठीक है, और उन मेटल्स की जो आइडेंटिटी है वो है उनका प्रोटॉन नंबर या एटॉमिक नंबर. मतलब
नहीं वो देखो ना, ये नॉर्मलाइज भी कर रहे हैं ना.
ठीक है,
हमने देख रहे हैं. हम अभी जरा इस बात को खत्म होने दो, फिर आपको सवाल का जवाब मिल जाएगा. ठीक है, तो लेट्स डिफरेंशिएट दिस विद रिस्पेक्ट टू Xi. Okay, so if you were to differentiate this with respect, so you're looking for minimums of this function, or extremal points of this function. So if I were to take this function and look for its minimum, three or five. So ये जो है 3 और 5, और 5 है ना. ठीक है, N E F फैक्टर ऑफ 2 भी तो आता है इस वजह से। ठीक है, so this becomes 1/2 NEF 1 plus gamma 5/3 minus 1 2/3 minus 1 minus gamma zeta 2/3, right? This is the derivative of the first term minus un square over 4 2 zeta, right? So I really want, so in the next step let's compute the average energy per unit atom, per unit electron inside the system. So for that case, I can divide this by small n, by capital N. I will get the energy per unit electron. So in that case, what we really want is I want this term to be 0. So I really want half one plus xi 2/3 minus 1 minus xi minus plus 2/3. I want this to be equal to u n 2 EF xi. UNEFA4. ये हाफ है, ये 2, सॉरी, ये 2. So this is my condition for a root to exist for the energy. Now this, let's call this, let's give this the very uninspiring name, left hand side, right hand side. Okay, and this thing over here is dimensionless. Everything here is dimensionless. So I have a dimensionless equation. So there's an energy here in the denominator, and we know that U is also an energy. It's that Thomas Fermi screen potential. So this is, all of this is an energy. Numerator must also be an energy. So what Stroner did, for purposes which just for a physical equation, a physicist thinks this way, he gives this energy a special symbol, or a special parameterizes this as kV times some temperature theta over EF. Okay, sorry. Okay. Now we would like to find out the roots of this equation. If a solution exists, then there is a likelihood that a minimum for this energy also exists. The second derivative is going to tell us whether it's a minimum or a maximum. So the right hand side is a straight line with respect to xi. This thing, if you plot this thing, it's a monotonic function. It keeps on increasing as xi increases. You can plot this, I'll show you in a plot at the very end. So now if I were to make a graph, I want to see where the two kind of lines, the left hand side and the right hand side, they intersect. So the right hand side is a straight line whose slope is k theta over EF. Right? K theta over EF. And the left hand side is a monotonic function. Monotonic function का मतलब ये कि as zeta goes up, the function also goes up. It's not a straight line, but very close to a straight line. But three scenarios can be identified. Let me draw those three scenarios. देखिए हमें ये वैसे किसी जगह पे मिलेगा नहीं 1936 के पेपर में भी बहुत टर्स है वो पेपर उसको मैंने सिंप्लीफाई करके मैंने समझाने की कोशिश की एक जसारत कर रहा हूँ तो दिस इज सिनेरियो 1 ठीक है सिनेरियो 2 सिनेरियो 3 the first scenario states that possibility is that the left hand side which I'm drawing in blue never intersects. Yes. Straight line is the right hand side. And by the way, you don't want to go beyond xi equals 1. That's your limit for xi. This is scenario number 1. So, I've drawn the straight line of slope k theta over EF. Scenario number 3 is that the left hand side never intersects. Possible. Right, okay. Given that the left hand side is a monotonically increasing function, which it is. We have proved that by looking at the slope of the left hand side. Right? So, in between, you can have a scenario in which there is a point of intersection. Right? So, there are three scenarios that are possible. So, the first scenario corresponds to the slope of the left hand side of this equation, of the derivative equation, being greater than the slope of the right hand side. Now the slope of this left hand side is 1/3. Now the slope is greater even at the starting point, at this point. So this is the slope of the left hand side at computed at xi equals 0 is इसकी जो slope है 2/3 1/3 1 2/3 नहीं आ जाएगी. The slope of the left hand side is 2/3 at xi equals 0. If this is greater than the slope of the right hand side, kb theta over EF, no solution to this equation exists. When this is the case, you do not have a minimum in this energy. You can plot this, you can verify this by plotting. So this is 0.666. When kb theta over EF is less than 0.666, you do not have any ferromagnet. You cannot have ferromagnet. You do not have a solution which admits a minimum in this energy. So you do not have ferromagnetism. On the other hand, if you look at this scenario is when the slope of the right hand side, which is kb theta over EF, is so large that the left hand side never has the kind of tenacity to intersect, it lags behind. And this is the case, and you can check this property that even at the extreme value of xi, the left hand side has not caught up with the right hand side. So if I, in this equation, if I put xi equals 1, I'll get this point is going to be un over 2ef. Right? This point is going to be kb theta over ef for xi equals 1. And this point is going to be, this term goes away. This is going to be 2 raised to power 2 over 3 divided by 2, which is 2 raised to power minus 1 by 3. So this scenario corresponds to kb theta over ef being larger than 2 raised to power minus 1 by 3, which is about 0.79. Now I'll show that this, even though this never intersects, if I plot the energy curve for a value of kb theta over ef greater than this value, I will always get a minimum in the energy curve at xi equals 1. I'll prove that in a minute. In between, when kb theta over ef is less than 2 raised to the power minus 1 by 3 and it's greater than 2 by 3, I get a point of intersection. And at that point of intersection, I have a non-zero finite value of zeta, which zeta is still less than 1, but it's non-zero. So this is the case when I have some spin polarization. Some spin polarization means I have a weakly ferromagnetic scenario. So this is weakly ferromagnetic. This case is when I have a zeta equals to 1 and I still have a minimum in the energy. This is perfect ferromagnetism. Strong ferromagnetism, perfect ferromagnetism. Now let's look at all of this graphically. In other words, if I were to make a phase diagram for this ferromagnetic behavior, so this is my value of z, this is 0, this is 2 over 3, which is 0.667, this is 2 to the power minus 1 by 3, which is 0.79. Here I have paramagnetism, no ferromagnetism, no spontaneous magnetization. I have weak ferromagnetism. And here I have complete ferromagnetism. Just at this point, I cannot up till 1. All right. And I'll explain this from a different perspective, but iron, cobalt, and nickel lie somewhere close to the ferromagnetic regime. Not entirely, but somewhere close, because I need to improve upon this model a bit. That model is called the Hubbard model. There are some materials like chromium, zinc, it's an alloy, that are weakly ferromagnetic and they lie in this regime. Copper lies somewhere in the paramagnetic regime. Alright, now let's explain this, let's look at this from a kind of graphical perspective. So really, by the way, this is not xi, this is kb theta over ef. Sorry. Okay. This axis is kb theta over ef. When kb theta over ef is less than 0.6, I get paramagnetism. For this model, Electrons might be in a band, but it's a kind of imperfect model. In between 0.66 and 0.79, I get weak ferromagnetism, and beyond this, I get perfect ferromagnetism. Because if my K theta over EF is greater than this value, I will always have a minimum as zeta equals 1. Let me show that, okay? Intersection देख सकते और K theta over EF को मैं A कहता हूँ for my computer code, ठीक है? Let's see. First of all, let me take my A to be 0.5, which is less than 0.66, right? The first transition point in the phase diagram. So I want to plot plot from zeta 0 to 1. First thing I want to plot is 1/2 into 1 plus lambda. 1 plus zeta by 3 minus 7. 1 minus zeta. Okay, that's the first thing I want to plot. Second thing I want to plot is A into zeta. Alright? So let me see if I can plot the legend. Got it? Now let's change this A to 0.6, which is still less than the first transition point. There's no intersection. No intersection. Now for this value, let me plot the energy for this value of A. That energy is E कहाँ मैंने लिखा है वो ये है ना इसको मैं अच्छा what I'm going to do is I'm going to plot so इसको मैंने n से divide करना ही करना है क्योंकि I want per electron so I can get rid of these n's. I'll be just left with one n over here and then what I do is I plot I plot E naught HF over over 5 NEF. So I get half 1 plus xi 5 by 3 plus 1 minus xi 5 by 3 minus un over 4 additional 3 5 NEF psi. Okay, so this really is 1/2 1 plus xi 5 by 3 plus 1 minus xi 5/3 minus 5/12 UEF xi, right? Now, let's express this in terms of now U एक और n स्क्वायर एक और n भी है अभी इधर, ठीक है, क्योंकि वहाँ un स्क्वायर था शुरू में. अच्छा, now all of this un over 2EF, this would become 1/2 1 plus xi 5/3 plus 1 minus xi 5/3 minus 5/6 un kb theta EF. Right? So this is minus 5/6 A into xi. So I want to plot this energy. Okay? For this particular value. So my energy is, I want to plot. तो दोबारा plot कर लेते हैं. Half 1 plus xi 5/3 jama 1 plus minus xi 5/3 minus 5/6, right? A into z. जो गलती है यहाँ पे ये है. ओहो, जाई नहीं है ये 1 plus I square, sorry. है ना? All right. So there is no minimum. The only minimum that exists at xi equals 0 means unmagnetized.
सर वो 5/12 है या 5/6 ही है
5/12.
वहाँ पे
5/6, sorry. 5/6 होना चाहिए ना? फाइव बाई सिक्स होना चाहिए, ठीक है?
ओके सर.
All right. So this is scenario number 1. Let's talk about the intermediate case, the weak ferromagnetic case. Now I increment A, kb theta over EF, so that it crosses 0.667. Still less than 2 to the power minus 1/3. Okay? So let me just kind of check what's the value of 2 raised to the power minus 1/3, 0.79. So it's between 0.66 and 0.79. Let's choose a value of 0.7. Now you can see that there is an intersection between the curves. Let me kind of zoom in onto this a little bit. So I 0.6 and 0.8. Right, you can see that point of intersection very clearly. Now for this value of A, let me plot the energy. It has to have a minimum. non-zero value of zeta, which is less than 1. So it's not perfect ferromagnetism, it's partial ferromagnetism. Let's see if I get that cusp. Here you go. I have a cusp at this particular value around something 0.75 or something, where the two curves intersect, and I have a minimum at that point. And I can check that for this value xi, the second derivative of my original energy is going to be positive, which indicates a minimum. So now for this value of xi, I have a stable energy, a stable equilibrium condition in which the energy is minimized. The system would like to go into that state thermodynamically, which means ferromagnetism is the spontaneous behavior for such a system. If my k, theta and EF are tuned in such a manner, which means that the Fermi energy and the interaction energy between the electrons is just at the right value. And I can express this in a more amenable form, which I'll do in a minute. Now for let me go beyond 0.7. Let me go at 0.75. I still should get ferromagnetism. Right now, the point of intersection very close to 1. So if I plot this up to 0.95, 99, right? You'll see that point of intersection. And then I plot the energy. I still have a minimum. For values beyond 0.79, so if I take this to be 8.8, this is on the rightmost side of the phase transition of the phase diagram, magnetic phase diagram, I do not get any intersection. So let me just kind of zoom in onto the really last part. See, there's no intersection. All the way up to xi, zeta equals 1. So I do not have a solution. But if I were to plot the energy, I can't go beyond zeta equals 1. So I plot the energy, it is going to have a minimum at zeta equals 1. So the system would tend to align itself in the perfectly ferromagnetic state. It will try to achieve that zeta equals 1 scenario. Right? So this is this is the Stoner criterion. That is k theta over EF has to be in a certain regime for kind of ferromagnetism to happen. This is right. Now if I ये 1 कब होगा जब ये 0 होगा और n plus is n. All the spins are of one kind. Okay, that's perfect ferromagnetism. Or the other way around, when this is -1, it will also be perfect ferromagnetism. So all spins of one kind. So in our previous lecture, we only looked at the perfect ferromagnetic case. So this is the in-between magnetic, and this is really the phase diagram. This tells us a little bit about the Stoner criterion. Now, I can recast the Stoner criterion in a different fashion. I have some bounds on k theta over EF. Now, if I look at k theta over EF, k theta or Boltzmann constant theta over EF is really un over 2EF. I want this to be larger than this value for perfect ferromagnetism. And this is an in-between case. So let's look at this in-between case. I want this thing to be larger than 2 by 3. I'll get some kind of non-paramagnetic behavior, some kind of paramagnetism. So if this is greater than 2 by 3, right, this is the condition for ferromagnetism according to the Stoner model, the classic Stoner model from 1926. Now, UN is this tells us about the correlation between the electrons. It is a factor that determines the Coulombic repulsion between the electrons. Now, I also do remember that the density of states at the Fermi energy is given by 3 over 2 n over Ef. Now, if this is per unit volume, this is also per unit volume. If this is not per unit volume, this is not per unit volume, but it's all consistent. Now, if I look at this expression, this means that n over Ef is 2 by 3 G Ef. Okay. So this means that Q over 2 n over Ef 2 by 3 GEF is greater than 2 by 3. So this really means that if my UGF is greater than some threshold value, this Stoner model gives us a threshold value of 2 or 1 or something. It depends upon what model you're using. So if it's greater than some threshold value, B, in this case, in this model gives us B equals 2, then you will expect that this kind of electronic system is going to give you ferromagnetism. Some kind of ferromagnetism. Okay? I just want to show one more slide, please. I forgot. The right hand side of this inequality equal to 1. Because so far what we assumed is that the kinetic energy of the electrons is kinetic h bar square k square over 2m. But that's not the case for band electrons. Electrons that are inside bands, that's not the case. They have other energies which are given by the energies of the Bloch states. If you remember your course from solid state physics, the electrons are now in Bloch states. Their energies are not quadratic or parabolic. So this model has to improve further if you really want to take into account band electrons or band magnetism. Now if you look at this curve over here, which is an adaptation from the original paper, 1936, Stoner had his paper in 1936, then there was a review of all these 3D transition metals and magnetism in these 3D transition metals in 1977 in another paper. So if you look at the top curve gives you the values of U's that come out from simulations on these 3D metals. The bottom curve gives you the density of states at the Fermi energy, GEF. So the band structures can be predicted from simulations. There are many techniques for predicting the band structure. One of them is density functional theory, DFT. So this gives us the density of states for atom, lithium, sodium, scandium, right? And then you kind of multiply the U with the density of states, and then you make a plot for the different elements. And this is the threshold which is given by the improved Stoner-Hubbard model. That is 1. You see that iron, cobalt and nickel cross this threshold. So if the density of states is large at the Fermi level, which is true for 3D electrons for iron, cobalt and nickel, or the potential energy per atom is large, per electron is large, or combined effect is that the product of these is large, then you can expect ferromagnetism. So iron, cobalt and nickel safely go beyond this Stoner criterion threshold. That's why they are ferromagnetic. Palladium as well as platinum, which is not shown here, is also very close to being ferromagnetic. That's why you can dope, you can have a matrix in which you dope palladium and make it ferromagnetic. It's very hard to have these metals turn into ferromagnets under any conditions. So it is these 3D metals which have precise number of electrons, and I'll show you what the band structures look like in the next lecture as well. Alright, so I think this is kind of gives you a good idea of why certain metals can become ferromagnetic. Now we want to improve this model a little bit. Okay, and or come up with an alternative model. So let's see how we can do that. Any questions? Just want to kind of do a quick appraisal of the Stoner-Hubbard model. In the Stoner-Hubbard model, we also have a kinetic energy term and a potential energy term. But the potential energy term is of the Hubbard kind. Now, what is the Hubbard-Hamiltonian? We've already seen the Hubbard-Hamiltonian. So let me first straight away write down the Hamiltonian in this model. So the Hamiltonian is given by H, is once again given by H bar square, A square over 2m, Ck sigma, Ck sigma, sum over k's and sigmas. Now there is an additional term. This represents kinetic energy. Now electrons are inside a band. So they are moving around in a band. That motion or hopping, which is also explainable by the tight binding Hamiltonian, is described by the kinetic energy term. So electrons can move around and hop between different sites. So that gives you kinetic energy, of course. And then on top of it, there is an interaction between the electrons. And that interaction is such that the electrons, two electrons that are on a site, one lattice site. If two electrons are on a site, they must have opposite spins. And now the itinerant electrons are not interacting with one another, but two electrons on a site, they are interacting with one another through a Coulombic energy. And since they are on the same site, the potential energy of the system goes up. Right? So we have an additional potential energy term, say of some constant magnitude u, given by the number of electrons on the site I, say of spin up type, and the number of electrons on the same site of the spin down type, summed over I. So this is the proposed Hamiltonian. This is the Hubbard term, and this raises the potential energy, whereas this is the kinetic energy. Now once again there is a competition between kinetic energy and potential energy. This is a term that corresponds to electrons being localized, spins being localized on atomic sites. This corresponds to itinerant electrons, electrons that are moving around. So this is an itinerant term, and this is a localization term. Alright, so far we've only looked at itinerant models, in which electrons are moving around and they are interacting with one another through the Coulombic repulsion. Alright, so now what we could do is we could have another theory, we could invoke another theory. Big capital N's. So, if you notice, one of these terms has spin up and the other has spin down. So they have opposite spins. Right? So let me look at this Hubbard Hamiltonian, and let me just focus on the summation part. U is a constant. So I can also write this as I, both sigma could be up or down, m I sigma n I sigma, where sigma minus sigma, right? So one is if this is up, this is down. This is down, this is up. Correct? Alright. Now, if there's another theory which explains lots of phenomena, that's an example of a mean field theory. And it's called the molecular Weiss, or the Weiss mean field theory, Weiss's mean field theory. It's a mean field theory. What the Weiss's mean field theory tells us is that I can replace, now this is an interaction between two electrons of opposite spins. What the mean field theory does is that it replaces this term, this number density operator, by the average number of electrons on side I with spin opposite to this. So it replaces the number operator with an average number. Alright? So this becomes, under this mean field theory, this becomes I sigma n I sigma. This just becomes an expectation value, an average number. This is an expectation value. N I sigma. Now if this is a real crystal lattice, this average n I sigma bar over all, so this is an average over all the I sites, all the lattice positions. So this will give me a number independent of I. This will simply be the number of spins, electron with spin sigma bar. It's independent of I because it's an average sum. So I can replace this with n sigma bar. It's a number. N I operator sum over I. Oh, sum over sigma, sorry. Okay, so this is a sum over I. Right? So this equals, in the next step, this would equal n sum over sigma this is a sum over all i's of a particular spin sigma. So at the end, ठीक है, इसको मैं आपकी आसानी के लिए this thing here ni sigma, of course this is ci sigma dagger ci sigma, correct? This thing, as you would all know, equals k ck sigma ck. Correct? You do the Fourier transformation, you get this. Now look at this term. This is prepended with this term. Sum over sigmas. There's a sum over sigmas here. So I can combine, I can make this Hamiltonian into quadratic form. Overall, my H becomes sum over k's, sum over sigmas, H bar square, k square over 2m, plus there's a u, plus u, n sigma ck sigma dagger ck sigma. Correct? Correct. This is a quadratic form, diagonal. So this is the average number of spins of the opposite kind to sigma. It's a mean number. If you apply a magnetic field as well, what's going to happen? This energy is going to change a little bit. So that energy is going to be added. It's going to be sigma ub b. Correct? Where sigma could be plus 1 or minus 1. Right? Sigma for sigma plus 1, this is plus mu b, and for the other term it's negative. Okay? So this is the Hamiltonian, and this is the energy of an electron of wave vector k and spin sigma. Yes, please. अगर हम मैग्नेटिक फील्ड ऑन करते हैं तो एनर्जी शिफ्ट बाय दिस अमाउंट इज द Zeeman term. So why have I added this energy? Because I just want to find out the susceptibility. I want to do two things in one go. I want to find the susceptibility of the system, and I also want to look at the Stoner criteria. Now this is my energy. Let's call this part E tilde. Now how do I find out the, suppose I want to find out the magnetization of the system. Is there a magnetization of the system even in the absence of a magnetic field? So how do I compute the magnetization? कैसे magnetization from scratch कैसे calculate करें? Let me just finish in 5 minutes. And I'm sorry for that, but very hard to kind of stop it here. So magnetization of the system, if I have everything per unit volume or not, this is mu b, the magnetization of each electron, n up and n down, correct? Now what is n up? N up will be dE G Fermi-Dirac E. What of my energy is for, this is for the plus spin, so this is E tilde plus mu bb plus u n minus, okay? I don't need to actually put in this expectation value sign here, but I can if I want. Okay? So this is the average number of spin up particles. particles. This is a Fermi-Dirac distribution function. This is the density of states at this new energy that we computed. Likewise, if I put minus sign here, I'll incur a minus sign here, and this will become u n up. Now look at the energies in the spin up sector. It's being determined by u multiplied by the number of spin down spins. So the spin down spins are creating an effective magnetic field in the spin up sector. This is the main field theory. Okay, and in the spin down sector, the spin up particles are creating an effective. Alright, so if I kind of now put everything into m, mu b, 0 to infinity dE, f e, I get g e plus mu b b plus u n, right, minus g e minus u b b plus u n up. Okay? Now I can use the Taylor series expansion. If I were to use the Taylor series expansion here, this will give me mu b. Now this is, as you all know, a step function. I use partial integration by parts. This will give me a Dirac delta function. All in all, I will get a g at EF, okay, plus some other things. Final result, just want to write down the final result. Please do this on your own. Is going to be two mu b square GEFB plus u. Now n up minus n down is going to give me another m. Right? Please do this on your own. Okay? Just remember that the difference of two objects, this thing minus this thing, that object is a function of. So all of this is going to be equal to the derivative of g computed at e tilde. This thing minus this, which is 2 mu bb plus u n up minus n down. Okay? This is the first order term in the Taylor series expansion. The final overall result, if I then find out the susceptibility of the system, chi, m is chi h. The overall result is this can you kindly do on your own, mu naught mu b square GEF 1 minus UGEF. This would be the susceptibility of the system. That's the final result. Please derive this from. Now, here you can observe that if UGF is much smaller than what? The numerator denominator. The numerator dominates. The numerator is in fact the Pauli susceptibility, polyparamagnetic. The material remains paramagnetic if UGF is less than 1, much smaller than 1. The numerator is the Pauli susceptibility. कोई शक नहीं है इसमें. ठीक है, अगर आप GEF को रिप्लेस कर दें 3/2 n over EF से you get the Pauli susceptibility. ठीक है. If this UGF starts to grow bigger, then 1 minus a big thing becomes smaller. This thing goes up, and then there's a divergence. When this UGF, this product UGF, this product becomes equal to 1 or touches 1, this term diverges. There's a divergence. That represents a phase transition. It's a second order phase transition in the language of statistical mechanics. It represents a phase transition. The material becomes ferromagnetic. The guy becomes larger and larger. At one point, it just tips off and it becomes ferromagnetic. So the Stoner criterion in the Hubbard model is that UGF, this thing, is greater than 1. Okay? And 1 over this term is called the Stoner enhancement parameter. So this is a better model than the primitive Stoner model, the Hubbard interaction, which includes this on-site repulsion between two electrons which are on the same site, gives you a better model, and it also incorporates what happens to electrons inside band. It's a more realistic model. So the next 2 lectures, which will be our last lectures before the final presentations, we're going to look at more detail and examples of the Weiss molecular mean field theory and see how different ferromagnetic phenomena can be explained by this description. So today, if you would like to send me your reports as a first cut, I can provide you with feedback before your 8th December deadline, I think, or 9th or 8th. ठीक है? अगर आप कुछ भेजना, आप मुझे भेज दें, मैं भी फीडबैक दूंगा, वरना फिर शायद फीडबैक देने का वक्त ना मिले. ठीक है, आपको शेड्यूल तो मिल गया ना सारे एग्जाम.